So now it is time for section 2.5. We are going to now learn how I can use this stuff kind of in the real world. And I say real world because in everyday life, maybe not, but if you get a job where like you have to deal with mass and work and that kind of stuff, you are going to use it there. And so I say real world because, going to the store, you are not going to need this, but in a job using math, you are. Okay. And so this stuff, once again, just like I've said, math always looks harder than it really is. This stuff isn't hard at all. So don't let it be harder than it is. Okay. And if you find it hard, that's completely fine. Just let me know. Okay. Because I don't want you to feel bad about it. I'm just saying don't make this harder than it is what I mean. Okay. I'm not saying it's not hard because technically all math is hard and this is Cal 2, so Anyway, but I'm saying don't make this harder than it actually is, okay? So, this first part right here, given a thin rod along the X. So what this means is it's just a horizontal rod. That's just horizontal. That's what it means. It's just a rod, okay? Horizontal rod. Let rho of X, this weird Greek P, is a rho. Rho. Let rho of X denote a linear density function, giving the density of the rod at any point X. Then the mass is going to be the integral from A to B of rho of X dx. So this is going to tell me the mass of the rod. Is what it is. And basically what it does is it tells me about each individual point, and it's just going to add them up, is basically what it does. So it's not too terribly bad. Example number 1, consider a thin rod over from pi over 2 to pi. If the density is rho of X equals sine X, what is the mass? So, using this, for example, number 1, our mass is equal to integral from pi over 2 to pi of rho of X. And rho of X here is sine of X. So I just got to do that. And that's it. So that's what I meant by don't make it harder than it is. This is something we have done a bunch of times, right? So using that. So all I've got to do is take the antiderivative of sine of X. We know that is negative cosine from pi over 2 to pi. Plug in our top bound first, which is pi. So negative cosine of pi minus, which makes it plus. Plug in the bottom bound. Cosine of pi is negative 1, so that's negative 1, plus cosine of pi over 2 is 0. The negative 1 just makes it positive 1. And that's it. So that's what I meant. I'm not saying that it's not hard. I just mean don't make it harder than it is. You know what I mean? It looks worse than it really is. Example number 2, consider a thin rod on the X from 1 to 3. If rho of X is equal to 2x squared plus 3, what is the mass? So it's the same thing here, okay? Plugging it into the formula. Mass is equal integral. The bounds tell me it's from 1 to 3 of 2x squared plus 3 dx. And this is something we did in Cal 1. So take the antiderivative of that. Do plus 1 here, makes it x to the third over my new power, which is 3. So 2x to the third over 3. Antiderivative of 3 is just 3x. From 1 to 3. Plug in our top bound. So that's 2 times 3 cubed over 3 plus 3 times 3. Minus, plug in a 1, 2 times 1 cubed over 3, minus 3 times 1. 3 cubed is 27. 27 times 2 is 54. 54 divided by 3 is 18. Sorry, that took me longer than it should have. Plus 3 times 3, which is 9. 1 cubed is 1. 2 times 1 is 2, so minus 2/3. Minus 3. 18 plus 9 is 27. Minus 3 is 24. 24 minus 2/3. We need a common denominator, which would be 3. So 24 times 3 is 72. So 72 over 3 minus 2 over 3 is 70 over 3. So again, make sure you know how to do these. If anything doesn't make sense, or if like you need any help with it, always let me know. So now I'm going to take the same idea, but instead of it being a rod, it's going to be a circle. So instead of it just being a singular rod, it's going to be a circle on the plane like this. The difference there is just like we did in section, I'm trying to go back, 2.3. This is where I do the whole 2 pi length thing, right? So this is exactly like what we did on the shell method. It's the same exact thing. So 2 pi times x times rho, and my top bound is going to be my r. So it's going to give you r, okay? So as an example, let's look at example number 3. Let rho of x be equal to the square root of x. Represent the radial density of a disk. Calculate the mass whenever the disk has a radius of 4. So, using the formula for my mass, it's going to be equal to integral 2 pi I can bring out front. So let's bring 2 pi out front. Integral 0 to r. So that's going to be 0 to 4 because it said r was 4. Of x times rho of x. Rho of x here was a square root of x dx. So this is something we have already seen in this class, so it's nothing too new. You know what I mean? X times square root of x, we have done that a few times. We know that is x to the 3/2, because this is like saying x to the 1/2 times x to the 1, so x to the 3/2. Antiderivative of that, add 1 gives me 5/2. Then dividing by 5/2 is like saying times 2/5. So 2/5 x to the 5/2 from 0 to 4. 2/5 times 2 pi is 4 pi over 5. Plug in a 4 first, 4 to the 5. Ooh, I did not write what example this was. This is example 3. So sorry about that. 4 to the 5/2 minus 0 to the 5/2. Didn't even need to really write that, but here we are. 4 pi over 5. 4 to the 5/2. Since I can do this one, I want you to, right? So square root of 4 is 2. 2 to the 5th is 32. 0 to the 5/2 is, of course, 0. 32 times 4 is 128. So 128 pi over 5 is what I get there. So again, this is exactly like what we did with the shell method, the same exact thoughts. So I'm going to do it again. For example number 4, let rho of x be equal to 3x plus 2, and I want you to find the mass when the radius is 2. So same idea. Mass is going to be equal to 2 pi integral 0 to the radius. Our radius we said was 2. So 0 to 2. X times rho of x, and rho of x here is 3x plus 2. So distribute the x. 2 pi integral 0 to 2. 3x squared plus 2x dx. Take the antiderivative. We would add 1, which would make it a 3 over 3, but what's nice about that is 3 over 3 is just 1. So this is just x cubed. Antiderivative of 2x is just x squared. 0 to 2. Start by plugging in 2. 2 to the third plus 2 squared. If I plugged 0 in, it would just be 0, so don't even need that. So I get 2 pi times 2 cubed is 8, 2 squared is 4, 8 plus 4 is 12. That should be equal. 8 plus 4 is 12, 12 times 2 is 24. So 24 pi. So one more time, don't make these harder than they really are, but if anything doesn't make sense, let me know, okay? Last thing for section 2.5 is finding the work. The work is done by doing the integral from A to B of the force. Now, what's going to make us do one more step is I've got to figure out what the force is, okay? So to do that, I use Hooke's law, which says the force required to compress or stretch a spring from a starting point to another point is f of x is equal to k times x for some constant k. So we have to figure out what that k is. Once I know what the k is, I can plug it in there and then plug the force here. So that's what I want to do, okay? So, example number 5, suppose it takes a force of 10 to compress a spring 0.2 meters from the starting point. How much work would be done to stretch it 0.5 from the starting point? So it's asking for the work. How much work? So I want to use this. But before I can use that, I've got to know what the force is. So I'm going to use Hooke's law to see what that is, okay? So Hooke's law says that the force is equal to k times x. I just don't know what k is. But what I do know is that the force is equal to 10 if I move it 0.2, right? So my force is equal to 10 when x, which is how far we want to move it, is equal to 0.2. So k times 0.2. That's what I know. Therefore, I can use this and solve it for k. So just divide by 0.2, divide by 0.2. 10 divided by 0.2 is 50. So what this means is I know f of x is 50x. So now I can plug that in and figure out what the work is. So the work is going to be equal to, now this is where some people aren't really sure what to put here. Notice that the bounds are how far I want to go. So the bottom bound is where I start. Since I'm starting at the starting point, it's going to be 0. And I'm going to stretch it. I want it to go 0.5. So my top bound is going to be 0.5. So I'm starting at the starting point, and I want to stretch it 0.5. And the function is 50x dx. This isn't bad, right? Take the antiderivative of that. You would add 1 to the power, which would make it a 2. So 50x squared over my new power, which is 2. From 0 to 0.5. 50 over 2 is 25. So it's just 25x squared. Plug in our top bound, 25 times 0.5 squared. Minus plug in the bottom bound, but since it is 0, doesn't really help us. So I don't really even need this. So I just got to do 0.5 squared. So you would do 0.5 times 0.5 and then multiply that by 25. So the total amount of work is 6.25 joules. So again, really the only hard part here is figuring out what the K is, but that's still not even that bad, right? Last one, example number 6. Suppose it takes a force of 8 pounds to stretch a spring 6 inches from the starting point. How much work is done to stretch the spring 1 foot? So do the same thing. In order to find the work, I need to know the function for the force. Remember, the force is equal to kx for some k. What I know is that the amount of force is 8 to stretch it by 6. So 8 is equal to k times 6. Divide by 6, you get 8/6, which reduces down to 4/3. So the function is going to be 4/3 x. So for the work, be careful here. Notice it's asking for 1 foot, which does not match what I put here, right? So this would actually be from 0 to 12 in order to match that, because 12 inches is equal to 1 foot, and they've got to match. So 1 foot means I'm actually going to put 12 up here. So 0 to 12 of 4/3 x dx. Take the antiderivative of that, add 1, which would make it 2, divide by that 2, 4/3 x squared over 2 from 0 to 12. 4 over 2 makes it 2, so this is going to actually be 2/3 x squared from 0 to 12. Plug in 12. 0 would give you 0, so I don't even have to. 12 squared is 144. 144 times 2 is 288. And I believe you can reduce that. 288 divided by 3 would be 96. So 96 joules there to move it foot. All right, so once again, I will say this 1,000 times. If anything doesn't make sense or you need any help at all, please let me know.